Here's what I want to do this lecture. I have 1, 2, 3, 8 things. Basically, we covered a lot of material, but in terms of concepts, here's what I want you to remember. So, from the beginning, we started with the Lorentz model. And remember, the picture was this. Basically, mass on a spring, except that now, so we call this an elastic constant. This is a mass. Except that now, the way you have to think about it is something like, I don't know, a molecule like this could have several atoms. And you will have charge plus, minus, something like this. That basically oscillates as you apply an electric field. So the charge times this electric field produces a force that is the driving force. And in the first order approximation, it looks exactly like the mechanical problem of mass on a spring, where you have a driving force like that. And it's kind of surprising that the equation of motion, writing the equation of motion for the electron, so something like this, minus E over M. It's amazing that this equation of motion actually tells us most of the optics, right? And if you remember, we started with linear systems, Fourier transform, such that now we are able to solve this equation of motion basically in one line in our heads without doing anything else. So I'm going to write the solution in the frequency domain by Fourier transforming this. So it's going to be minus E of omega over M times 1 over, and now here we have omega naught squared minus omega squared minus I gamma omega. I don't know if you should really copy this one more time, because it's all kind of reviewing the notes, but okay, so basically you should now know how to solve any linear differential equation, in particular this one. It's very easy. What did we use here? That x dot Fourier transform of that is minus I omega. That's the square, that's minus I omega times gamma. Boom, this is a solution in the frequency domain. So how do we go from here, displacement at the molecular level, in the electronic displacement at the molecular level, how do we get to something macroscopic, like refractive index?
Take the real part.
You?
Real part for the refractive index.
I don't know why I can't.
You take the real part for the refractive index.
Take the real part, okay, but this is still a microscopic thing. How do we go to the macroscopic? In other words, if this is my volume and it's full of 10 to minus, to 10 to plus 20 of these, what do I need to do? Yeah, I need to average them out, okay? So in the first approximation, first of all, the induced dipole is something like E times X, right? So charge times displacement, that's the definition of a electric dipole. And now I have a bunch of them in a volume V. The induced polarization will be just the average of that over the entire volume, which, if we assume they are all oriented in the same direction, which is the first order approximation, will be something like so this is the volume density. So it's the volume density of those dipoles times P of omega. So this induced polarization now, so basically we just added all these, right? So you have a bunch of these like that. Millions and millions of them. That's what happens when you shine light on a piece of glass, right? You induce dipoles along the direction of the electric field, and those re-radiate. Okay? Now, this P is a macroscopic quantity that actually goes in Maxwell's equation. Right? So that is basically the connection. From this displacement, I get the induced dipole, induced polarization, and now from here I go to chi of omega, and from here I go to n of omega. So chi is 1 plus epsilon r, which is 1 plus n squared. So from here I get the refractive index. But notice, all this thing does is to add some prefactors here. The line shape of chi or of n is basically looking like this. So from here I'm going to have n prime of omega as the real part and n double prime of omega as the imaginary part. And you should kind of know how this line shape looks like. So the absorption part will have a maximum, right? Which is at the resonant frequency omega naught. Okay, as you know, the resonant frequency is actually something to do with the elastic constant. Do you know the relationship? Do you remember from high school? What's the resonant frequency of a spring? Huh? 2 pi over k. That's a different k. No. This, let's call this kappa or something. Is the elastic constant.
Square root of that over.
Square root of that over m. Okay, omega naught is square root of k over m. Right. Okay, so that's what this means. So basically the line has this very kind of characteristic shape. This will be, let's say, chi double pi. And now, or let's call it n. And the real part is what we generally call refractive index. Right? In common English, when we talk about refractive index, we mean real numbers. But technically, there could be an imaginary part too. So now there is this function that looks like this, that is now symmetric with respect to the one line here, that goes like that. What do we call n of omega? That the variation of the refractive index with frequency or wavelength, we call that what? Dispersion. It's all in here. Okay? So this curve that is funny looking like that, that tells you everything there is to know about that material. Except that in real materials like this, where are the most important resonances in this material? UV. And there are several of them. So basically, a real material like, let's say, transparent material like glass, has a bunch of maybe absorption lines here in the UV. Nothing much invisible, right? Because otherwise it wouldn't be transparent. But it's also, the dispersion is not that huge. Keep in mind, these are always related, right? So the highest dispersion, the highest derivative of this, happens around the absorption, under this absorption line. So basically in the visible, you still have something like this, right? So these curves that do that. So that's how the dispersion will look like, and that's how the absorption will look like. I'm sorry, invisible. So that's why sometimes we did later calculations where we assumed that this dispersion is something like omega squared. Because basically we see this tail that could be approximated as a parabola first. Are you with me? Okay, so that's how we explain something like this. It's all from this little equation of motion. Again, something that we didn't do, but you should keep in mind, when you have multiple resonances like this, the effect at a particular frequency is the result of all of those. In other words, you may have tails that come from all these three lines that may contribute here. Okay? Okay, so roughly it would be nice to remember this. The way I'm thinking about these courses like this is kind of from my experience as a student. So now I have the experience of saying what sticks with you 10 years later. Right? So if you don't remember a formula, that's okay. You can always go open the Saleh book again, you'll find it. But I remember stuff, explanations from high school, from my physics teacher. Just hands waving conceptual things. Those are the things that stick with you. So that's what I'm hoping with this. So beyond all the equations and stuff, if you can assimilate the light-matter interaction with the kind of this mechanical problem of mass on a spring, then everything else will follow. Okay, and this is, by the way, this is a much more general problem of having a combination of real part of the response and imaginary part of the response. And I gave you a few times the analogy in fluid mechanics, for instance. There's always a viscous part, an absorption part that dissipates energy, and there is an elastic part in fluids. So in many branches of physics, you will see the exact same problem. There is always a dissipation and a storage property. Okay, let's move on. Unless you have any question about this. So 2 is geometrical optics. So kind of the way we went through these classes to go from simpler to more complicated. That's what I think we should do in undergrad courses, although there's a bunch of grad students here. Well, in grad courses, it's kind of, you can go top down, start with the more general and then branch it into different things. So what do we expect here? I want you to be able to ray trace any problem involving lenses or curved mirrors, objects like this. You should be able to not only draw the rays, find the image, but also calculate anything that is relevant, magnification, positions, whatever. Then, so I would call this ray tracing. Okay, so you should know that this should go through the focal point, for instance, things like that. If I have a point at infinity, you should know where that goes. Simple things like this. And then, you should know the matrices. Okay, so we have translation matrix, we have a refraction matrix. You combine these, you get the lens matrix. And you should be able, you should know how they get multiplied, the proper order, and so on. And if I give you a system of 7 lenses and whatever, you should just at least put them together. So that the computer can do it later. Okay? Now, the idea of imaging, I want you to kind of have a good understanding in terms of the concept of imaging. What does that mean? So if I have a specimen or a sample, whatever here, that either emits light or I illuminate it with something, doesn't matter. An imaging system, it's let's say a black box, microscope, telescope, whatever. Imaging is mapping point by point the sample onto the image plane. So that point will be image here. So you see the imaging system is doing the time reverse of that emission. And if you remember in the matrices, there is a very kind of nice way of obtaining the lens equation by setting the condition that the rays for imaging, they all converge in one point, meaning that this y is not a function of the angle theta. Remember, the matrices are in terms of this distance from the optical axis, which we call elevation, y, and angle of the ray with respect to the horizontal. Condition of imaging means that y is constant with respect to theta, right? If I was in this plane, which was out of focus, that wouldn't be true, right? Look what I'm getting there. I get various points for various angles. So if I remember correctly, that gives you a b equals 0. And from that, you get something like 1 over x prime plus 1 over x equals 1 over f for a simple lens. If this is a lot more complicated an imaging system, then whatever it is, b equals 0 will give you the imaging condition. Okay? So first you need to know what imaging is in words. It's taking a point from here and mapping into a point here. The map follows immediately. Okay?
So you're saying that all rays coming from your sample
All right.
at any theta are going to 1 watt.
1 point
Okay.
in the image plane. And of course that is a perfect image. Which we call, these are the conditions of stigmatic image. So that's an ideal condition. It's kind of never like that, but as we learned in wave optics, that actually this point is not a point, actually it's more like a spot, and this spot depends on how many angles I allow in. Okay? So then we go into details, but the concept is this. Point in a sample, point here. Y is not a function of theta, that gives you the imaging condition. Okay. So talking about wave optics, what do we want to remember 10 years from now? And when I say 10 years from now, I refer to those who don't go into optics careers. Those who now choose to go on a music path or something. Because those who are going to do a PhD in optics, they will know a lot more than we did in this class. Hopefully I'm going to see some of them in spring. So what do we want to know? We want to know how to solve Maxwell's equation. And I gave you the simplest recipe I know on how to do that. So starting with the Helmholtz equation, right, which is something like this. R and omega. So always try to keep the variables. That's kind of important. Now, beta squared of R and omega, U of R and omega, equals 0. How do we solve this? We add here a source, right? There's no field unless I have a source. How do I solve any linear problem? I replace my source with a delta function in space. And let's say there is no omega. So it's an amplitude. This is a point source if you are in 3D. Right? So in 3D it's going to be a point source right here. But now, if I'm in 1D, I only have x-axis. Delta of x means this wall, infinitely thin, that is placed as the origin. Right? Can you picture that? This wall? And that is emitting light. Both this way and that way. So, what is the solution for the 1D? An infinite plane source will give you plane waves. Okay? So there is no reason why you will have any curvature of any kind, since this is an infinite wall. So basically you're going to have plane waves going this way and going that way, minus kx. How do we solve that mathematically? I take the Fourier transform of this. I know that the Laplacian gives me minus k squared. This beta is homogeneous. There is no function of r. So this becomes 1 over something like beta squared minus k squared. And I simply, that is the solution in the k domain. I take the Fourier transform of that. I get the solution in the spatial domain. And it turns out this is something like e to the I k x times x. And in 3D, you need to know the Fourier transform of that thing in 3 dimensions. You can work it out, work out the integral. But basically, what you're going to end up in 3D is with a spherical wave. So k is the modulus of the wave vector. R is the radial distance from the origin. And this tells you that basically it's spherically symmetric, as you would expect to the point that is by itself in the universe. And also, it goes down as 1 over r. So you have these waves going from the origin outwards, but the amplitude has to go down as 1 over r. Intensity as 1 over r squared.
My intuition would tell me that it should go as like 1 over r squared.
The power goes as 1 over r squared.
Okay.
The field is 1 over r. So your intuition is good.
So what about in 2D?
Huh?
Is it
Okay, 2D, the same thing. You have a plane that is confined in 2D. I mean, you have a point source that is confined in 2D. So it's like delta of r in 2D and delta of z. Right? It turns out this is a little trickier, but you solve it the same way. So delta in 2D will still be 1. This will be k squared, but now you are in 2 dimensions, so it will be k associated with this. I can put it here rho if you want, where rho is square root of x squared plus y squared. Right? So symbolically, all 1D, 2D, 3D, they kind of look the same way, like 1 over k squared minus beta squared, something like that. The difference is when you take the Fourier transform back. In 1D, it's a one-dimensional integral. So e to the I kxx times 1 over kx squared minus beta squared. In 2D, it's basically a Hankel transform. So it's a radially symmetric 2-dimensional Fourier transform. And in 3D, it's a spherically symmetric integral. And there is a funny thing that happens with the 2D that I don't want to get into now. So the 2D, I mean, you can kind of tell it's weird a little bit, the 2D case.
So it's
And it's not so common in practice, but there's a discontinuity that happens. I don't want to get into that. We'll do it next semester. Yeah.
So does the plane wave have like a neat form like it does in 1 and 2D, or is it weird? Like, I mean,
Why don't you do this integral and you'll find out. So the integral is 1 over beta squared minus, I call it k perpendicular squared, where this is kx squared plus ky squared. And take the integral of this of j naught of k perpendicular rho k perpendicular dk perpendicular. So this will give you the 2D solution that I will call U2D of rho. So the same separation, I remember I did this, I prepared recently something, and this separates in 2 terms, but there is a step function that I remember comes on top of this. I think in ultrasound people call that a wake. Have you heard of this? Okay, if you're interested, look into this and we can discuss it offline. You're not going to see it in the exam, okay? 2D is slightly more weird than 1D and 3D. All right. So, I mean, everybody knows this, right? I'm sure you knew this before you joined the class, that spherical wave looks like that, or plane wave looks like that. But now I think hopefully you'll see it easier how it comes from the wave equation. There's now no magic for it. I don't like it. Most textbooks say you can verify that if you plug this in here, it's a solution, as opposed to just solving it. Anyway, so what's the more useful stuff we do with this? Well, in the lab we deal with 3-dimensional problems, and basically we found out that if I take the spherical wave like that, and I'm writing this as x squared plus y squared plus z squared. So I'm looking at these spherical waves around this center, and I'm looking farther and farther and farther. So I'm kind of looking at these narrow angles. We can have a kind of a very useful approximation to this sphere. Instead of a sphere, I can think it's pretty much a parabola. Okay? So instead of a circle, I say it's a parabola. This is the Fresnel approximation. Why do we like parabola so much? Because if you have something like e to the I x squared plus y squared, I know how to do the Fourier transform of that. Believe it or not, that's why we like Gaussian so much all the time. We try to make it look like a Gaussian, sometimes even if it doesn't look like it, because we can calculate easily. So the Fresnel approximation is doing this expansion here, which is, so if you factor z out, you get something like z square root of x squared plus y squared over z squared plus 1, and then you Taylor expand that, so it's z over 1 plus whatever over 2z. Something like that. This doesn't have the proper units, like that. Yeah, so with this z, we know it's going to be x squared plus y squared over 2z. But basically, the picture is this. I take a spherical wave and I approximate it with a parabola if I'm far enough away from the source. The even more drastic approximation is basically to assume that this is pretty much flat here. And that is the Fraunhofer approximation. And this is very useful because if I have my initial field here, U1, and I'm looking far away, Z Fraunhofer, here I get something U2 that is proportional to the Fourier transform of U1. And if you remember the way, if I call this coordinate x2, the Fourier transform of U1 is something of K1 x, K1 y, let's say, where K1 now is x2 over lambda z. Okay, so in real life I have this problem, let's say in the final. Just say, you have this grating or something, diffraction path of some kind of diffractive object, a transparency with something. And we're asking what's the, the field distribution in the Fraunhofer region. Mathematically, it's a Fourier transform. But now, how do you exactly map this Fourier transform to a plane here to have proper units, like 1 centimeter from the origin? What is that going to be? Well, this is a transformation. So the frequency, the spatial frequency is actually x2, this, over lambda z. So you see, as z goes farther and farther, basically you're left with more and more of the center region of the Fourier transform. Right? So this scales up, gets broader and broader.
Times 2 pi.
If it's k, yes, probably. Talking about typos. Hey, don't get confused, 2 pi, okay? Okay? The even more useful result was that I can do the same thing by actually placing a lens exactly a focal distance after the input plane, input field, and looking exactly 1 focal distance behind. Same thing. Difference is now K1 is 2 pi x2 over lambda f. Right? And right here, this is the basis for Fourier optics. The fact that now I can make a Fourier transform in a kind of a compact space. I make the Fourier transform here, now I can add whatever I want, some filters, and then I add another lens and I do another Fourier transform. Basically I get the image back, U1 prime, right? So this becomes the basis for doing optical filtering of any kind. Fourier transform here, I don't know, if I want to low pass it, I block the high frequencies, high pass it, I do the other way around. Add the second lens, boom. Optical filtering at the speed of light, basically. And if you forget everything, remember what the difference between this filtering and the digital filtering on the computer, which is what? The phase. The fact that this Fourier transform is for electric fields. If I take a picture of this, whatever this might be, and then Fourier transform that and do everything else in the computer, in MATLAB, I can, but I may get very different results. Most of the time I will. Meaning, this filter operates in the field, in complex fields. Once you took a picture of this, this becomes an intensity. Fourier transform of a modulus square of something is not the same as the Fourier transform of that something, of that field, right? So that has to be very clear. So basically, this frequency domain treatment is basically the most efficient way of analyzing an imaging system. Any imaging system, whether it's a camera, microscope, telescope, because we learn a little bit later that actually this frequency content, the distribution of light here in the Fourier plane of that lens, essentially tells you the final resolution, right? That you will be able to resolve from this plane. The finer the details I want to see here, the larger the angles that I need to collect. Okay? If it's not showing up here, in other words, you miss this lens, in other words, this is the highest frequency component, that will correspond to a particular sinusoid in the object, which basically we call that the resolution limit of the imaging system. Okay? So, two ways of doing Fourier transform. Just let it propagate or use a lens. Of course, this is more practical because sometimes to go to the Fraunhofer region requires maybe kilometers of propagation, right? Depending on how big your source is and so on. While this doesn't. All it requires is that you match these distances carefully. So I just mentioned that, like any other linear system, the frequency domain, the analysis should be done in the frequency domain. Now, what's the picture in your mind when you're trying to propagate a certain field, let's say in free space? So I have this source, and I want to know how this light propagates far away. How do I think of this in terms of linear systems?
Think of it as point source.
Superposition of point sources, right? So, how do I write that? S of x and y, or r, is integral of s of r prime delta of r minus r prime d to r prime. Right? So this is mathematically, it's just a simple property of the delta function. But physically, you see, it's very heavy. It tells me that any distribution of any source, any distribution of field, usually by source we mean, all the time, we mean either primary source, something that really has molecules that emit light, or a secondary source, which could be, that screen where it emits light only when it's illuminated. Either way, I can think of these as point sources distributed at different points in space. So why is this important? This is a convolution, right? So S convolved with the delta function. Why is that important to write it like this? Well, because I know how the light propagates from each of the point sources, right? I know actually it's going to look like this. Right? So It means that in the far field, I'm going to have U of r prime as the convolution between S of r, I can have r everywhere, vector, convolved with H of r. That's all. And that, it's an unpleasant operation. So now we replace the response of the delta function with that, and you end up with this convolution in 3D. It's not very nice. But if I look in the frequency domain, this is actually a nice product, H tilde of k. And that makes you wonder, hey, in order to get H of r, this, I solved the Helmholtz equation in the k domain first. Then I brought it to the r domain. Now I'm bringing back to the k domain again. And believe it or not, that's what most of the books do. They start with this, because everybody knows this. What I'm saying is, we should start from here. So plus beta naught square S of r. If we take the Fourier transform of that, we have minus k naught plus beta naught squared u of k and omega equals S of k. Basically, u of k and omega is already this. So this is how the field diffracted from an arbitrary source looks like everywhere in space. No approximation. Except that it looks unusual because it's in the k domain. Right? So you see, if you want to go back to the r domain, what do you have? You have a product between S of k and 1 over this. This gives you the spherical wave. This gives you S of r, so you get back a convolution. But if you want to keep it in the k domain, that's it. That's full solution, no approximation. So I think this is kind of underutilized in our everyday work, but that's a different story. So this is the essence of the Fresnel-Huygens principle. Okay, so Huygens in the 17th century came up with this idea that, you know, like watching the surface of a pond, how it oscillates, these points at the next points in oscillation, and you have a wavefront that's kind of the tangent of that, and then the next point in oscillation, and so on and so on. It took a couple of hundred years to have Fresnel to actually formulate that mathematically, but basically now, even later, we understand that it's nothing more but the linear system kind of treatment. Break the source in point sources, add all the point sources, I know how each works. My system is linear. It's going to be a convolution between, you can think of this, the impulse response of the vacuum, right? Spherical wave is the impulse response of the vacuum. Convolve with the source, whatever it is. Right? So if you spell this out as an integral, that is called a Fresnel Huygens integral. If you approximate this with the Fresnel approximation, so you make this into a parabola, that is called sometimes a Fresnel transform as opposed to a Fourier transform. Are we comfortable with this? Right? Okay then. Okay. coherence. Why do we need this nuisance in our life? Well, the reason is that not all the points from a source oscillate in phase. And it means that the light is never purely monochromatic, meaning delta of omega minus omega naught, or delta of k minus k naught. This is a, what is this? What will be a field that has this distribution in k? 1k. Plane wave, thank you. So that's a plane wave. And this is a, what do we call this? Monochromatic light. Okay, they don't exist. There is always a delta omega, the width of the frequency distribution or wavelength distribution, and there is always a delta k. And that's the problem. So coherence deals with these statistical properties of the fields. The fact that rigorously we need to take ensemble averages whenever we deal with real life fields. What happens in the lab usually is that we don't worry too much about that in regular experiments, because this is narrow enough for our practical purposes, and sometimes this is narrow enough. So really we don't need to worry too much about it, except that when you do interferometry, that becomes quite important. So one simple way I want you to think about this is that, imagine I'm asking the question, if this is not a monochromatic light, it's not minus I omega t, I cannot write it like this. But what would be the average e to the minus I omega t, provided that I have a distribution p of omega? So I have a spectrum, right? Like this light here has a spectrum of light. So it has a certain weight for each omega. Can I define a spectrum weighted exponential like this? Yes, I can. It's basically integral of p of omega e to the minus I omega t d omega, where I normalize this such that integral of p of omega d omega is 1. Right? I can do that. But what is this? What is this integral? Of p of omega, which is autocorrelation, gamma of tau. So you see, even though we have a broad bandwidth, the autocorrelation function is basically telling me, on average, how that field behaves. So kind of a strange definition for the autocorrelation function is kind of a spectral average sinusoid. I can do the same thing in the spatial domain, right? E to the I k r, and it's an integral of p of k e to the I k r. So let's say we're in 2D. So that's spatial autocorrelation. Same thing. So in other words, for monochromatic light, my field looks like this. For broadband light, it starts to look like that. That's an autocorrelation in my drawing, and that would be a monochromatic light. So the way I look at this, at the coherence, is in a kind of a global way. You can define an autocorrelation that includes both time and space. But most general, commonly in the lab, we don't worry about both at the same time. So for instance, we do low coherence interferometry, we only care about the temporal aspect of the coherence. And we keep the light well behaved in space, meaning we make a plane wave, we couple it into a fiber, so the spatial component doesn't play a role. So that's why I'm sure some of you don't like the notes, they look a little dry and heavy on the notations especially and so on. But basically what I wanted to say is that let's fix K. So we say W of K, and this is fixed. And I'm looking now only at tau. So that will be low coherence interferometry, for instance, or temporal coherence. And then let's do the other way around. I fix omega, and I'm looking at the spatial variation. Okay? So it's always all the equations are very symmetric. But the bottom line is this. I have a correlation time, or coherence time, which is basically defined as the width of this autocorrelation function. And it's basically, depending on your definition, it's the inverse of the spectral bandwidth. So the coherence length is speed of light times that. And I have a coherence area that is basically lambda, that's kind of 1 over delta K squared. Okay, so delta K is this spread in the K vector. And it's an area, so that becomes squared. It's basically lambda over theta, everything squared, maybe with some 2 pi. So it's lambda squared over the solid angle. Lambda squared over capital omega, where this is solid angle. All right? So this is the bandwidth, delta omega. This is the spectrum. And now, spatial coherence is all about extended sources, right? And the coherence of the field emitted at this distance is going to be something to do with this solid angle. Okay? That's all. I narrow that solid angle down. I essentially increase the correlation area in that plane of observation. And in the lab, I can actually do a very good job at narrowing this down by doing what we call spatial filtering. So imagine I can take a lens. So if this is your source, I can take a lens, do a Fourier transform. This is F. This is F. Fourier transform. And now cut the pinhole here and only pass the center part. Once you do that, basically, it's as if here it looks like a plane wave as opposed to, possible wavefront delays and structure in the wavefront. Okay? That's all. The rest of the math, I think there's a graduate coherence course taught by Scott Carney once every other year or something. So there's a whole course on that if you're interested in it. But for experiments, that's what you kind of need to know. If you want to do an interference, you want to keep your delay within this. If you're doing some kind of spatial correlation where you're doing interfering a point from here and a point from here in a given plane, you want to make sure that you stay within that. Otherwise, you won't get any interference. Okay? Are we okay? Yeah, okay. Well, that silence doesn't sound good. So why did we need to talk about coherence at all? Well, because for one thing, there are microscopy methods that use that, treat the image as an interference process. It's a coherent process. And one way to get contrast is to use the phase information from the field. And for that, you need coherent fields. But before that, a straightforward application of temporal coherence is low coherence interferometry, where you want now your coherence gating, your coherence length to be as short as possible, such that you can probe various surfaces. The light is reflecting from these surfaces like this. And if you're interfering this with a certain plane wave, let's say these are overlapping, and I'm scanning a certain mirror, well, let's make this into a mirror. And I'm scanning this over this distance, I will start to get interference once the mirror matches one by one these surfaces. The resolution with which I can solve those surfaces is exactly given by the coherence length. So that's why for high longitudinal resolution LCI, you want low coherence, low temporal coherence, meaning broad bandwidth sources. OCT, optical coherence tomography, is basically LCI applied for imaging. Okay, so LCI, by the way, this is the geometry. I hope you remember that. But you worry me that you're copying so intensively as if you've seen this for the first time. I was hoping we will be more discussing and stuff. But, so if this is the sample and these are the surfaces I'm trying to solve, basically I'm adjusting this mirror up and down. And here at the detector, I get the superposition of the two. And the intensity is going to look like this. Bleep, bleep, bleep. OCT takes this idea and makes it into a 3D imaging system. So you have the Z, the depth. All you need to do is to scan these beams somehow over all these, over X and Y. Well, the depth is given by this scan. And there we go. What did we learn about autocorrelation and spectrum? They're the Fourier transform of one another, right? So if my signal in LCI or OCT is basically it's not autocorrelation, it's cross correlation, but Fourier transform of cross correlation is also cross spectral density. So gamma 1, 2 of tau, Fourier transform of that is what we call W1, 2 of omega. So U1, U2 conjugate of omega. So if I'm interested in this, I can do it by definition, scanning the delay. So this adjusts the delay tau. Or I can put here a spectrum, spectrometer, and I fix this at delay tau naught. Get the spectrum, Fourier transform, that gives you the signal. The advantage obviously is that this is much faster. I don't need to mechanically scan anything.
What if you split the source and
That's under the same idea. So I can put a spectrometer here, or I can put back my detector, and now I sweep the laser. I don't know how to show this. It's like a variable omega. So this laser is putting out a range of frequencies, one at a time. And the technology is so good today that this sweep could be very, very fast, like 100 kilohertz or more. I don't know, what's the fastest now?
Okay, the other guy works on it.
Okay. So you see, it's the same thing whether you send all the frequencies and you measure with the spectrometer or you send it one by one using a detector, but basically this is better, I think. The signal is better, the signal for each line is stronger. This could be faster than a spectrometer. So I think for fast, this swept source SSOCT is, I think, now top of the line. So there are two ways to do frequency domain, and the old way, the time domain of scanning the mirror. What's the resolution? So let me tell you something. I had a couple of bad encounters in qualifier exams and things like that. I mean, bad experiences. Because questions like, what's the resolution? How do you define resolution in a microscope? Comes out. And not necessarily from me, from somebody else. So my advice is that that shouldn't take you more than 50 milliseconds to answer. Otherwise, when they look and you see you took 460, I saw people that took the next course, which is the microscopy course, and they had the pause when they were asked about resolution. So that really looks bad, I'm telling you as a...
Bad on you or?
Huh? It looks bad on me too, right? So, I mean, what are you guys doing? But they cannot. Okay, so it's important in OCT to realize that this resolution, the longitudinal one, is nothing to do with the numerical aperture, right? It's the coherence time, the coherence length. So that makes it special. While the resolution in a microscope, right, it's all about the numerical aperture. Even the Z resolution in a confocal microscope, which we're going to study next semester, it's all related to the numerical aperture of the objective. But this, you can actually get very good sectioning in Z with collimated light, meaning zero numerical aperture. It's because the encoding is different. It's this interferometric optical gating that relates to the correlation function. That's why you want it narrow and broad spectrum. Okay, so let's move to microscopy. And this is number 6. So in any imaging system, and that's for qualifiers, that's a kind of a standard thing. There are two things that we are going to be asked about. One is resolution. One is contrast. The resolution part is more clear-cut than the contrast part. Meaning, how do you answer the resolution in a microscope, if you're asked right now? What do you say? What is resolution?
The ability to distinguish two adjacent points.
The ability?
To distinguish two adjacent points from each other.
Okay, so the smallest distance between two close points. Okay? Good, that's the definition. Now, okay, show me quantitatively what that means. What does that depend on? Then what do you do? Take the chalk and you look in the frequency domain, right? That would be impressive. I mean, it would be nice to explain that. So I'm trying to resolve this. The finer structures will scatter light at larger and larger angles. So for instance, you can make two sinusoids here. And then the objective will be my first lens, and it's going to do a Fourier transform right here. And you can tell, well, the problem is that this has a finite size. Therefore, in this frequency domain, this has a finite size. That's the maximum frequency. Right? And then you can act smart. If I have a square aperture or triangular aperture, I can answer that. But basically, you should know it for a circle, as for a disk, right? So what's the diffraction figure for a disk? What is the diffraction pattern coming out of a disk? What's the Fourier transform of this? First of all, we should call this something like a filter or transfer function, right? So the transfer function of my microscope is a disk that blocks all this light except for this circular pattern, right? So I can write it as a circ of R over whatever, W or B. So basically, in the frequency domain, I have my field U of k times this transmission function of k in 2 dimensions. So when I put my second lens, or if you want to get fancy, if I go back in the sample domain, right? Probably that's easier so you don't use magnification. So I take the Fourier transform this, I go back in the spatial domain. That will give me the version of the object. And usually I put a bar here to say that it's not my original field, it's actually the filter field by my objective, which is my perfect field, U of R, Fourier transform of that, convolved with a Fourier transform T tilde of that. I mean, it looks kind of straightforward now, but for whatever reason, in the qualifiers, I've never seen somebody to logically start from here and write it up to here. I don't know why. Beats me. Like a coherent 5-minute presentation on resolution. Makes such a good impression if you can kind of in 2 minutes explain everything. If you know how to say it in words, that will still be good. That 2 points minimum distance, that's good. But now, if you're able to write something, draw a picture and write an equation, in particular here you end up with something like lambda over 2na or 0.6, 1, whatever, then that's perfect. But then if you're able to even write this, then I think you pass the qualifier right there. People will be so impressed that, but it's simple, I mean, right? Right now it looks very trivial. But for whatever reason, in a year or two, it's going to look very blurry. This convolution here will be fake. Okay, so to finish here, the Fourier transform of this is what? Right, so it looks like this, if you don't remember the formula, but basically it's J1 of whatever this radius is, right? So B times R over R. And now you're talking about, well, what do you mean by resolution? Which criterion do you want me to apply? Do you want me to apply the Rayleigh criteria or? And then the Rayleigh criteria means the second point, maximum of that overlaps to the minimum of the first, meaning the first root of this function. Okay, and that's something like 1.22, depends on the pi's and the variables, but basically the smallest thing will be something like this. And physically, again, this numerical aperture is the sine of the maximum angle. So this theta sine of this theta max is the numerical aperture. And the physics is that any sample can be thought of as a superposition of gratings, right? The Fourier decomposition. At some point, you reach a grating that is, the period is so small that is going to shoot past by the lens. That's all. That's all the physics. Simply, these fields don't fit into your objective. Okay, how about the contrast? What is contrast in general? Difference in intensity, right? So between what and what? So I signal minus I background, and I take a modulus to make it positive, and I call this contrast. That's a good starting point. So I have an image, I have a cell or whatever, and this is my object of interest, this is the background. Okay, so now, it would be nice to remember if you're asked this at the qualifier, or in the final, for that matter. What's the effect of the noise in the background? Hmm? So you see what the problem is? If I add, instead of IS, a pure signal, I add a big noise, N1, and this is N2. Even if I have zero contrast, IS minus I background is equal, let's say, I get the difference between the noises. So it looks as if contrast is very big, but actually it comes from uncorrelated noise in the signal versus the background. Do you see what I mean? So imagine your signal is this, plus noise 1, and the background is I background plus noise 2. And I subtract these two and I make I signal and I background equal. So I end up with the difference in noise. And if the noise is different here versus here, when you take the modulus of this, could be a big number. I mean, it's the bigger the noise, the bigger the contrast looks like. Which means that this is not a sufficient definition unless your noise is small. So that's why we introduced contrast to noise ratio, which takes this number, takes the contrast and divides it by the standard deviation of the noise. So you see in that case, in this particular case when there was no contrast, there was no contrast between signal and background, but the definition gave you some contrast. When you take the ratio with the standard deviation, you get something like 1. So you know that that's not good. Okay, so, but these are kind of definitions. This works equally well for the X-rays, MRI, whatever. Yeah?
Well, how do you define noise? I mean, sometimes noise are in features that are kind of hard to tell.
Well, it depends on your method, okay? I mean, there is no, I cannot answer that directly. If you're doing OCT, the noise in your image basically would be a patch that you know in your image, would be a domain that you know has no signal in it. So for instance, what we do. So the general problem is like this. I have my object, and I illuminate it with this plane wave, let's say, A incident. And usually what the field right after the object, I can write it as U naught, this plane wave thing, times the transmission function T of X and Y of the object. And for transparent objects, that looks like U naught times e to the I phi of X and Y. And no amplitude. I mean, it could be a constant amplitude, A, but no function of X and Y. So that means when I take the intensity, modulus square of this is actually U naught squared A squared, 0 contrast. No X and Y dependence. Right? So, you remember what are the two main contrast mechanisms?
Yes.
Hmm?
Yes.
Okay, the two main types of contrast. Two classes. Bright field and dark field, that's still under one class. External, so, or exogenous, and endogenous, or intrinsic. Okay, what does this one do? Exo means outside, endo means from inside, right? Staining any contrast agents from the outside. But essentially, from our little optics problem here, what does that do? Right. So even though your cell, as is, has only phase information, basically I'm adding contrast. If you stain it, you add colors that you see in intensity. So you make basically this a function of A of X and Y. So you make them from phase objects to amplitude objects. Good. And we didn't talk too much about this because I was telling somebody at MIT last week who's a fluorescence expert. I said, in my class, I tell my students that actually fluorescence doesn't belong to optics. It's more of a chemistry problem. Do you agree with that? And he said, no. I mean, he's a very good optics person. But so I still think that the active research here is in designing new molecules, better tags, more specific, higher quantum efficiency in fluorescence and so on. But in terms of imaging, there is nothing really special. So all the optics and the history of microscopy is kind of in here. So the idea is to go from phase into amplitude. And that's when you guys were saying dark field, and then what else?
Phase contrast.
Phase contrast. What else? DIC. Schlerin. All these kind of, so chronologically I think this was 1, maybe 2, 3, 4. And kind of GFP is kind of in the middle, you see? The green fluorescent protein, the 2008 Nobel Prize in Chemistry. What does that do? You take a cell to intrinsically manufacture protein that is fluorescent. That's kind of nice, falls kind of in the middle. Okay, so I expect that you know the optics of all of these, basically, what it means, and you know how to design a phase contrast by now. Right, any questions here? So more specialized techniques in spring. Next one is polarization. So in polarization, I expect you to know what an ellipse of polarization is, how that is obtained, what's the meaning of that. So the trajectory of the electric field, basically eliminating the time between the two equations on X and Y. That gives you an ellipse. And the ellipse collapses to a line sometimes when there is a certain relationship between the phases of the two components. And the ellipse becomes a circle when, I expect you to know when the two components are equal and pivotal out of phase, right? And then wave plates, which is our way of controlling the polarization state. So most commonly we have quarter wave plate, half wave plate. The half wave plate allows you to rotate an original linear polarization to any desired angle without loss of energy. That's kind of a big deal, right? And then quarter wave plate allows you to go from circular to linear and so on. Combination of the two allows you to do pretty much everything, right? Finally, anisotropic media. I expect you to know, so these are anisotropic materials. I expect you to know what uniaxial and biaxial crystals, and I also expect you to know the basics of electro-optic effect, what that means, and the basics of acousto-optic effect. And the Bragg condition, which you have for your homework anyway. Hey, what happened to the evaluation forms? James promised me to. I'm glad we didn't nominate him yet for any award. That's it. If you don't do the evaluation now, that's it, right?
Come on. Oh, we can do it on Friday.
Yeah, so can you go downstairs and get some evaluations? I completely forgot. I was planning to leave you 10 minutes, but can you go downstairs and at the department head's office and get the evaluation?
do it online.
Send us a link.
Huh?
Just send us a link, we can do it online.
You can? Okay.
Would they give you one right now?
I think so.
Because normally they're
Okay, I'll get it. Do you have 5 minutes or not?
Just give it to me. I'll give it to me.
I'll come with you and then I won't come back.